Okay, so in this lecture, we're just going to talk a little bit more about acids and bases and a little bit about pKa, but we're not going to do any of the math that you would have done in general chemistry too. No calculations, just have to understand the concept. So if we take this molecule, acetic acid, which is what's in vinegar, so which hydrogen, right? So which hydrogen is most acidic? So if you remember, what's the definition of an acid? An acid is a proton or a hydrogen donor. So we got 4 hydrogens. Which one's most acidic? So hydroxide is a base. So what it can do to this molecule, so let's see. You could use those two electrons on hydroxide to make a bond to this hydrogen, and the 2 electrons in the OH bond could become a lone pair. So now that oxygen is negative, and the oxygen on hot water is now neutral, right? If you calculate the formal charge, 6 valence minus 2 lines minus 4 dots is 0. Or this oxygen, 6 valence minus 1 line minus 5 dots is -1. Okay, so is the hydrogen on oxygen most acidic? Or is it the hydrogen on one of the hydrogens on carbon? So conceivably we could take, well, it doesn't matter which hydrogen, they're all the same. So we could take any of these hydrogens, so make a bond from oxygen to hydrogen, and then we're going to take the 2 electrons in the CH bond and make a lone pair on carbon. So we're drawing what's called a mechanism. A mechanism uses arrows to show how electrons move in a reaction. So if you notice, so I take the lone pair and the arrow goes to the hydrogen. That means we're taking that lone pair and making a bond to hydrogen. And then if you notice for this arrow, the arrow starts on the bond. That means we're taking those 2 electrons and the arrow head ends up on the carbon. That means we're adding a lone pair to that carbon. So now we would get this. And so now that carbon is negative. And then we made a water molecule. Okay, so which happens? Acetic acid is an acid. It loses a hydrogen. Which one does it lose? One of the 3 hydrogens on carbon or the hydrogen on oxygen? So hopefully you said the hydrogen on oxygen. So why? Why does it lose the hydrogen on oxygen? Well, in the process, you create a negative charge on acetic acid, right? So is it better to put the negative on oxygen, or is it better to put the negative on carbon? And of course, it's better to put the negative on oxygen because oxygen is more electronegative than carbon. So the most acidic hydrogen in that molecule is the hydrogen on oxygen. So that's usually the way it works. The hydrogen on the most electronegative atom is the most acidic hydrogen in a molecule. Okay, so another way to look at this, if you assign partial charges, which of these hydrogens are partial positive? And it's going to be that one, right? That hydrogen's partial positive. These hydrogens are not partial positive, because the electronegativity difference between carbon and hydrogen is very small. But the electronegativity difference between oxygen and hydrogen, right? Oxygen's 3.55, hydrogen's 2.20, big difference in electronegativity. So the most acidic hydrogen is always going to be the one that's most partial positive. Okay, so if we took these 3 molecules, HOCl, ClO2H, ClO3H, and HClO4, which is the most acidic. Well, so obviously only one hydrogen in each molecule. Which hydrogen is the most partial positive? And it's going to be that one, right? That's got big partial positive, and that would be smaller comparatively. Why? Because oxygen is electronegative. So its pulling electron density off of the hydrogen, and chlorine's electronegative, its pulling electron density as well. So here you have an extra oxygen pulling electron density. Here you have 2 extra oxygens. Here you have 3 extra oxygens that are all pulling electron density off of hydrogen, so that's going to be the most partial positive and therefore most acidic. Or if we compare these 3 molecules, which hydrogen is most partial positive? Well, it's going to be that one, right? That's big partial positive, a little bit smaller and a little bit smaller, because chlorine's the most electronegative, and then bromine, and then iodine. So that would be the most acidic molecule. Right, but those molecules are not very interesting to an organic chemist. Why not? Well, there's no carbon. They're not organic molecules. Although certainly we do use these molecules to do organic reactions with. Okay, so if we took these 4 molecules, which one has the most acidic hydrogen? And that's going to be the one, right? Fluorine's electronegativity is 3.98, hydrogen's 2.20, oxygen's 3.55, 2.20. I can't remember nitrogen, it's around 3, and carbon's 2.55. So the biggest difference in electronegativity is between fluorine and hydrogen, so that would be the most acidic. Okay, so if we take these 2 molecules, which one's most acidic? So first of all, which hydrogen is most acidic? It's the one on oxygen in both molecules. So if this undergoes an acid-base reaction, so water can take off a hydrogen from the alcohol, and then the OH bond becomes 2 lone pair electrons on carbon. So you would make H3O plus, hydronium, and the conjugate base of the alcohol. And for this molecule, so what kind of functional group is that? So if you've memorized your functional groups already, you have a C double bond O with an OH attached. That's carboxylic acid. And this is just an alcohol. So same basic reaction. Oxygen takes a hydrogen from the OH, and the OH electrons become a 3rd lone pair on oxygen. Okay, so that would be your conjugate base, plus you make H3O plus again. Okay, so which is more acidic, the alcohol or the carboxylic acid? And you can kind of figure that out just from the name, right? This is an acid, so it's going to be fairly acidic. But why is this more acidic? One way to think about this is, how about compare the conjugate bases? So which negative on the conjugate base is more stable? And the one that is more stable is going to be the one that's easier to form. Well, so on the conjugate base of your alcohol, so 100% of the negative charge is on that oxygen because it has nowhere to go. But for the other molecule, so the conjugate base of acetic acid is acetate. So for that, does 100% of the oxygen set on that oxygen? And the answer is no. Why not? Because you can do this, right? You can take a lone pair, move it there to make a double bond, and you can take a double bond and make a lone pair. So each oxygen carries 1/2 of the negative charge. So the negative charge is said to be delocalized. So what is that we've just done? So hopefully you've watched all of the videos from chapter 1. So if you've done that, then you recognize what we just did is drew a resonance structure. So anytime that you can do localized charge, right, anytime that you can do localized charge, it is more stable. So this acetate is more stable than the conjugate base of the alcohol. So it's easier to form. So if acetate is easier to form, then that means the acid, the carboxylic acid, is more acidic. So this hydrogen is easier to remove. Therefore, it is more acidic, because that's the definition of an acid, right? It's got to be able to lose a hydrogen to be an acid. Okay, so lastly, for this lecture, if you remember from Gen Chem 2, how do you write equilibrium constant expression? So it would be the concentrations of products. So concentration of acetate times concentration of H3O plus divided by concentration of reactants, and then we leave water out of the expression, right, because water is pure liquid. So products, it's products over a reactant. Okay, so the more products you form, the bigger Ka is. So the stronger the acid is, as acid strength goes up, right, Ka goes up because there's more product and less reactant, which means the acid has given up its hydrogen. And then if you remember, what is pKa? How's pKa defined? It's the negative log of Ka. And so as acid strength goes up, pKa is opposite, it goes down. So the lower the pKa, the stronger the acid. The higher the Ka, the stronger the acid. The lower the pKa, the stronger the acid. So if we look at the pKa for these two molecules, so alcohols have pKa's around 16, which is about the same as water. That's not surprising, right? They both have OHs, and they're not next to pi bonds, so you can't draw resonance structures. Whereas a carboxylic acid has a pKa of around 4, and that's a logarithmic scale. So the difference in acidity, pKa, is about 10 to the 12, which is huge, right? So pKa of 16 versus 4, about 10 to the 12. So that's actually a huge number. So carboxylic acids are a lot more acidic than alcohols are. Okay, but we're not going to do any calculations with Ka or pKa or anything like that, or pH. You just have to understand what pKa is and understand the concept. And so here basically the concept is that resonance increases acidity because the conjugate base of a carboxylic acid is resonance stabilized. You can delocalize the negative, but the conjugate base of alcohol is not resonance stabilized. That negative charge resides on oxygen, and there's no place for it to go. Okay, that's all.